Thanks for having me for this talk. This is a lovely venue and it's a lovely association. I've really been enjoying the other talks over the last couple of years since I found out about Nova Scotia Institute of Science. So it is lovely to join you this evening. So I'm going to talk tonight about some of the work that I've been doing in various parts of Canada and through the lens of what rocks can really tell us. So one of the things that I remember most from my very first year in Cape Breton was I met my first class of students. It was a small class. One of the students was from Eskazoni, and we are in Mi'kma'ki here on the unceded territory, and it was really nice to meet some students who are Mi'kmaq. And one of the things she told me in the first couple of weeks, she said, you know, this is kind of interesting because in my family and in my culture, we call the rocks the grandfathers. We call them the grandfathers because they tell stories. And she said, this geology thing is very much the same, isn't it? And I said, yes, that's exactly what they do. So rocks tell stories, and I wanted to share some of the interesting stories tonight with you. So I did grow up in South Africa, and it turns out I actually grew up in probably some of the most classic geology locations there is on the Witwatersrand in the gold mining area, right on the edge of the biggest impact crater on Earth. And I knew absolutely nothing about it. I walked over it my entire life and didn't know a thing until I hit first year university in Canada and discovered this world of geology. So I had spent most of my time being a classical harpist. So a little bit different. I still play and I still do concerts, but it's a little bit of a different audience, but it's still good. So I've been working in Cape Breton and in Nova Scotia. I did my PhD at Carleton, and I didn't actually start out doing a geology PhD. I started with an undergrad in science. I already had an undergrad and a master's in music and thought, you know what, I want to try the science thing. And I knew about 3 kinds of science, and it was biology and physics and chemistry, because there are no other kinds of sciences, right? So I took all of the first year courses, and then I had a hole in my schedule and I wasn't terrifically keen on taking physics because I had already done A-level physics, and there was this geology geography 6-credit course over a year, and I signed up for it and I never left. I kept taking geology courses and stayed for a PhD and then stayed for a job, and yeah, I'm not going anywhere. So it was quite a revelation when I first started with it. So one of the really important things that I've learned about geology is that scales matter a lot. Physical scales, so just sheer size, and time scales. So I wanted to go back a little bit today into the really big, long time scale of Earth's history. And all of the work that I'm presenting here is done with a whole army of other people. I'll highlight some along the way, but none of us work in isolation, and especially in geology, there seems to be quite a bit of a team effort in most cases. So thank you to a lot of people who are involved. So this is our sort of standard geological timescale. This is the IUGS classification of time. And if you've seen it before, you'll know that it is not linear at all. So it's managed to compress most of Earth's history into this section here. So this column here essentially represents the vast majority of Earth's history. I like this version much better, where we see it as a clock. So in this one, Earth forms over here. We go through all of this time, all of this time, all of that time, and right about here, animals start appearing. And just before you hit midnight on the clock, a couple of seconds before midnight, humans show up. So this I find is a very nice visual of how much of Earth's history we know less about. So when we think of Earth as a big system, some of the questions that we have as geologists center on when did modern processes, when did the processes that we see, when did those start? And how far back in time can we trace those processes? How can we figure out if what we're seeing today is the way it's always worked, or if things have changed along the time? So is our present the key to the past, or is it the past is the key to the present, or it's sort of a chicken and egg kind of thing? So some of the processes that we'll talk about tonight are some of those questions. So when we think of Hadean Earth, so this sort of beginning part, we think of basically a molten, very, very hot, very no liquid water. And then eventually around here, it starts cooling down enough to have a solid crust, to have some liquid water, to have an atmosphere, all those good things that we need. And then it just spends a whole lot of time cooling down. And we don't know a lot about those rocks because there are very, very few of them on Earth preserved today. But when we get into the sort of young part of Earth, once animals show up, these are closer to the surface. These are the things that we see a lot more of. These are, if we want fossils, this is where we find them. So this is sort of this last 500 million years or so of Earth's history is stuff that we're much more familiar with. So some of the parts that I'm interested in happen in this sort of transition area between figuring out where we were as a very, very low, inhospitable place, how things change into that Proterozoic era. So that really, and again, you can see that's most of Earth's history. So that's the part that we're really curious about. So when did modern plate tectonics start? And it's during this period that we saw Canadian shield and all the shields of the continents be assembled. So when we look at Earth like this, so this is a image that shows different kinds of mountains. So we have different kinds of mountains. Those form by colliding different things together. So parts of continents, island arcs with continents, smushing them all together. So here's India going into the Himalayas. There's Africa and Europe creating the Alps. There's our Appalachians. So that part, of course, used to be attached here. So those are mountains. And then where we see what we call shields, these shields are the cores of the continents. These are the areas that have been preserved since the Proterozoic. These are 2.5, 3 billion year old cores of the continents, and they've lasted through all of this time. So they tell us a lot about those early processes. So this is the Canadian shield, and this is what it looked like 1.8 billion years ago during the formation of a supercontinent we called Nuna, or Columbia. And this was one of the earlier supercontinents in Earth's history. So this is what we think of as mid of Canada. The slave cratons up here, Ray, Hearn, and I'm going to concentrate on this little area here. So you can see we were attached to Greenland, which was attached to Siberia, which was attached to all of what's now Scandinavia. So all of these continents were together at the time. And what we have in here in the red outline is the origin of the mountain event that put all of this stuff together, the Trans-Hudson. And it was a huge origin. This was on the scale of the Himalayas for sure. And there's lots of little origins stuck into it because nothing is one big composite thing all together. So in here we have a New Quebec origin, and in here we have the Tornadets. We have a really interesting area of Canada right in the middle there. So what happened before that supercontinent? Well, you had to break up the previous supercontinent. So when continents form, they stabilize for a while. That insulates the mantle underneath them. They start getting hot, mantle plumes come up, they crack open the continents, and the continents drift on their way. And eventually they collide with other things, and the cycle goes over and over. So in the Proterozoic, that cycle is about 500 million years long, from one supercontinent, break up, drift, till you assemble another one. So we're about halfway through a cycle because the Atlantic opened 200 to 250 million years ago. It's in the drift phase. Eventually we'll all meet on the other side of Earth. So in this period, we're looking at lots of mantle plumes, lots of activity to break up that earlier supercontinent. And it's probably called Kenorland. This is one of the ones that we understand a little bit less about because it's so long ago. But the thing that's interesting to us in here is this period of continental rifting. So this is solidly in the Proterozoic, and we are very curious to see what kind of processes would have been involved in continental rifting. So I'm going to show you something from the northern New Quebec origin. And that's an area that looks a little bit like this. So we have our New Quebec origin here. We have a little continental fragment, and we have the whole North Atlantic craton. And if you see this before the rift, just imagine Greenland is sitting right there. This is what it looks like today, but during this time that I'm thinking about now, Greenland would have been attached right there. So it's a really interesting area. This is a satellite digital elevation model. And when we were mapping in here, one of the things that sort of caught our eye was this pattern in the elevation. So we started looking at these, started landing on them with a helicopter, and found that kind of thing. So this is a picture from the NASA Earth Observatory, and it was actually one of their sort of photos of the day at one point. These are what they look like in when you're flying up to them. So there's these very, very large columns of basalt. When you land at the top, you see those perfect hexagons. You see layer after layer after layer of these basalts. So these are really, really stunning. They're composite basalt flows, there's sills, there's sediment in between them, and they all have this wonderful columnar jointing. This is really characteristic of the types of rocks that form when you split up a continent and there's a huge voluminous outpouring of magma. And this is the sort of thing that you see in the North Atlantic igneous province. When the Atlantic started splitting up, this is what it did. Huge outpourings of basalt. We see it everywhere in the world. So these are really remarkable because they're actually probably the oldest flood basalt province on Earth. It's the oldest preserved one. These are 2.1 billion years old. I'm going to show you some of the textures of them. So that's about as perfect as it gets. So columnar jointing forms when you have a flow of lava that cools, and as it cools, it contracts a little bit. It makes those beautiful columnar joints. Mud does the same thing when it cools. It makes those six-sided hexagons. So you can see how absolutely perfect these are. Right? There's nothing deformed. There's nothing strange about them. And every ridge you see up to the background is another set of these flows. These are huge. These are absolutely giant. So there's flows on top of each other. There's flows on top of sediments, which is what you would find in a desert or in an ocean when you pour lava all over it. You can see in that bottom layer that the contact is a little bit wobbly. So as the basalt comes over, it erodes a little bit into the sediment. So this is exactly the sort of thing that you would see in a basalt flow today. And the textures are beautiful. This is a volcanic bomb where you have lava erupting into cold water and it makes a little bit of glass and it makes these fragmental textures. And if you look at them in thin section, they're absolutely pristine, beautiful. This is glass, it's volcanic glass. So this is volcanic glass with little dendrites in there. And this is as fresh as it can be. If you take a sample from Hawaiian volcanoes today or from Iceland, this is the exact same texture you're going to see. So 2.1 billion years ago, these processes were operating almost exactly the way they are today. So this is a really fascinating area. And this is a map of some of the other flood basalt provinces in the world. Some of these are famous: Colombia, flood basalts, the Siberian traps, the Deccan traps. And interestingly, the designation traps is an Anglification, if that's a word, of the Dutch word for trap. And it means step, because all of these are stepped up and they look like stairs. That's where that word trap comes from. Here's another famous one, the Giant's Causeway in Ireland. So this is the young baby version. This one opened with the Atlantic, and it looks exactly the same as that one 2.1 billion years ago. So we have a really good set of a whole bunch of data that really says that at this time, we're documenting a continent splitting up just the way it would today. There's continents doing exactly the same thing today. Ethiopian rift has very similar structures, same kind of thing. So there's the, it's really nicely outlined in the snow there. So that's one really interesting set of, and that's a good picture of the steppe nature of it. So that's a really interesting thing that happened on that particular side of the origin. And of course, the question is, well, what happened after that? This was this huge continental breakup. What was the thing that happened afterwards? So we're going to go to Schefferville, which is right down in the corner here. And this is a digital elevation model of the Schefferville area. 10 points to whoever guesses which one is the mountain belt and which one is the craton that it sits on. Pretty obvious difference, right? This is the old part of the craton, and these are all the sediments that are accreted to it. So what was happening at this point, you can see really well in Schefferville. So when you get to Schefferville, this is the airport, this is the first time you see. When you've never been there before, you're like, oh, I wonder why. And then you realize, iron. So Schefferville is one of the largest iron deposits in the world. If you drive a car, there's a very, very good chance that part of the iron for that car came from here. If there was a car made in North America in the last 60 years, the iron probably came from there. So why that's, and this is the only operating mine that's there right now. The snake thing here, that's one train. Pretty impressive train. So these trains go down to Setu, the iron gets loaded on barges, and then it goes all over the world. So how do you make that sort of thing? As an ore deposit, you have to concentrate elements. So we have lots of economically usable elements everywhere. We have gold in seawater, 2 parts per billion. If you dried up all the seawater in the world, you would have a ton of gold, right? We can't do that. You need some sort of natural process to concentrate the ore, same as when you go lobster fishing. Like, you don't pick them out one by one, you put a trap down and you wait for them to concentrate themselves. So there's always a mechanism that's involved in concentrating and preserving those elements. So for most cases, you have to dissolve it from somewhere, you take it where it is, you transport it, and you have to put it down in a safe place, in somewhere where it's going to preserve. And at that point, if you can do all 3 of those things, you may have an ore deposit. So why would that have happened in that Schefferville area? Interestingly, the other equivalent giant iron deposits in the world are all the same age. The ones in Australia are the same age. The ones in Minnesota are the same age. The ones in Siberia are the same age as these Labrador traps. So what happened in that case was, after this huge outpouring of magma, after the continent split, you created what looked essentially like today's passive margins of the Atlantic Ocean. So you still have some island arcs, right? Think of Japan maybe as this island arc, and here's China over here. And in these back arc basins, we started seeing black smokers. So today, black smokers, hydrothermal circulation through the ocean crust, they dissolve elements, water circulates through, it hits cold seawater and starts depositing things. And with this huge outpouring of mafic magma that created those traps, it started changing some of the ocean chemistry. So we have black smokers and hydrothermal circulation that picks up iron and then oxidizes it and then deposits it on the seafloor. But we didn't have enough oxygen in the ocean to oxidize and rust everything. Some of that iron gets deposited in its reduced state. So at that point, we start producing these huge iron formations everywhere on Earth where you had large basins. So part of that is happening right around here, 1.8 billion years ago. So when we started making the first really big passive margins, one of the things that happened was that our prokaryotes, so bacteria, had places to live. They had places where they could stabilize, they could be stromatolites, right? They could be algal mats. What all of these algae started doing was producing oxygen. And in this period between 2.5 and 1.8 billion years, we started building up enough oxygen in the atmosphere to have an atmosphere that was a little bit more similar to the one that we had today. And if you're a paleontologist, that sort of 1.8 to 0.8, they call them the boring billion, because very little happened in terms of paleontology. You had single-celled algae at the beginning, you had single-celled algae at the end. For tectonics, though, it's fascinating. Lots of things happened for us. So it all depends on what you're interested in. But as you go through periods of Earth's history where these things change, you really start making new environments. When you have new environments, you're going to have new things colonizing those environments. So even something as remote as algae and flood basalts, they're still linked, which I think is quite interesting. Things that happened in that Labrador Trap area afterwards, this is pillow basalts today. These are pillow basalts that are 1.8 billion years old. Again, very, very similar. So you can see how this used to be ocean crust. You just stack layer after layer after layer of pillow basalts on them. So we know quite a bit about how the ocean worked at the time. So that's kind of the short geological history of an area like this. Big continental breakup, you make these wonderful flood basalts, and then you move on to modern sedimentary processes where you're making pillow basalts, exactly the same sort of thing that would be happening on the bottom of the Atlantic around Iceland or in the Red Sea today. And when we do that, we also create mineral deposits. If you're flying over a lake somewhere in the Arctic and you see colors like that, you know something is leaching out of those rocks. It's very, it's really quite obvious that there's metal there, and this is completely natural. Nobody's ever touched it, but it's still there. So our rocks catch quite a bit of this material and keeps it until, of course, something happens to it. So those are two really, really large scale, like continental history scale stories. What about some small ones? So this is a photomicrograph. This is what we see when you look at a rock under the microscope. And it's taken in what we call cross polars, which means your light is polarized and gives you really fancy colors. We use those to identify minerals and to look at structures. So for some slightly smaller stories, we're going to shift over to Cape Breton and a little bit of mainland Nova Scotia. So these are the questions that Anne mentioned at the beginning. What I really work on is, where do rocks come from? How do they get to the surface? And how long does that take? So to do that, we have a whole bunch of tools. Always start with field work. That's something that I do a lot of. And then one of the things that I want to show you is a little bit of geochronology. So that's how we date rocks. So that's how we know when a geologist tells you something is 2.1 billion years old, well, how did you get there? How do you get to that step? So we study metamorphic rocks for that because they're great for recording information. They record structures because they often get squeezed and deformed. They also record pressures and temperatures because minerals are stable at different conditions. And usually if we start increasing the pressure and temperature, we're burying the rocks, and then they form rocks, minerals that are stable at high temperatures, high pressures. And then when you pick them back up again and you exhume them, that's where you record cooling and decompression. So you're bringing them down into the crust and taking them back out. So these metamorphic rocks really record a lot of information. And Cape Breton is fantastic because it actually records a ton of information about different parts of the Appalachians. So when the Appalachians were all one mountain chain, this is kind of the setup that we had. The southern US Appalachians were here. What is now Africa, Northwest Africa here. We have Nova Scotia, we have little bits of Northwest Africa attached. We have Newfoundland here in the middle, then we have Spain. We go all the way through Scotland and England and up into the Caledonides and into Scandinavia. So again, this is a very, very long mountain chain. It was assembled when Pangaea was a continent, and then eventually it broke up again. So Cape Breton is neat because it actually has 4 different sort of parts to it. It has little bits up here that were attached to the North American continent. It has two terrains that really formed as arcs that came from Western Africa. And it has another one, Albilonia here, that was another Gondwanan arc that traveled all the way across the ocean for it. So there's lots of different spots in here and lots of different things that are recorded. So if we go to sort of the middle of Cape Breton here, the Boisdale Hills area, I just want to show you some of the rocks in there. So this is one called the Frenchvale Metamorphic Suite. And when it formed, Cape Breton was probably low latitude, fairly tropical in climate, fairly warm, could have had, if there were palm trees at the time, it would have had palm trees. And now we see it as these metamorphic rocks that are marbles and amphibolites. And these started life as limestones, beach sand, and basalt flow. So really you were looking at a Caribbean type environment in this place. Here's some of the rocks. They're quite attractive, really quite beautiful. You can see a lot of them do have some alignment in the minerals, and that's usually what you get when you deform things. Also has what we call Cape Breton rubies. These are corundums, and those form very particular environments. These guys are pink, so they're quite beautiful, but they're rare. It's the only occurrence that we have, but they're quite prized just for collectors. They're not a commercial ruby organization by any means, but we like them. We're quite fond of them. This is what they look like in section. So the stripy bits are the actual corundums, and the rest is other minerals living with it. And then we have some really high temperature gneisses, and we know where they come from. So we have a pretty good idea of where they form. And these are some of the pictures from them. So what do? How do we date things? Well, we generally rely on mass spectrometry. So the idea that you can separate ions by mass and you can count them. So we count relative proportions of uranium versus lead, because uranium is radioactive. It decays to lead. It takes a certain time. We can count the proportions and figure out how much time has passed. So in the system that I use a lot, we actually take our little minerals and we put them in an epoxy puck. We polish them off nicely, and then we stick them in front of the laser and we blow them up. It's great fun. And when you talk to classes of 8-year-olds, you say, what do you do all day? Well, today I blew something up with a laser. It was 30 microns big, but they're still impressed. So in this case, your laser vaporizes part of your sample. That sample material travels up tube. It goes into inductively coupled plasma. It gets ionized and then into a mass spectrometer that counts it. So that's the basic setup of what we would need for that. So when we date these little zircons, these are zirconium silicates. If you have cubic zirconia earrings, they're basically the same thing, except without the radioactivity, which is great. So we can use these in a number of different ways. We can date an igneous zircon and figure out when the rock crystallized, so when that thing became a solid. Zircons are great because they're resistant to weathering. They don't weather easily, so they will last. So the oldest zircons that have ever been dated are 4.3 billion years old. So they're just a little bit younger than Earth, so they can stick around that long. When they're igneous, they often have zoning, they often have sharp points, but when rocks erode, they take their zircons, and those zircons get put into sediments. So we can date the zircons in the sediment and figure out where the source for that sediment was. That's another way we can use them. We can also date them as metamorphic minerals. So sometimes you have an igneous zircon and it gets caught up in a rock that's going through metamorphism. And at that point, it will grow little metamorphic roots. So I can date that center and figure out how old the original rock was. And I can date the overgrowth and figure out when the metamorphism happened. So it's a really handy tool. We can do quite a lot with it. So this is just a little image from a paper showing some zircon dates. And in this case, all of the dates from the centers of the zircons was old, 1.1 billion, 1.2 billion, older than that. And all the overgrowths were young, 550. So we figured out from that, that this rock Its original source was quite old. We don't know exactly how old, but we know that it went through high-grade metamorphism at 550 million years ago. So what do we do with that? Well, here's a couple of examples. So these are igneous dates, so right in that Boisdale Hills area that I showed you. So we've dated some of these 560 million years, 540 million years. So at this time, this little bit of Cape Breton was sitting above a subduction zone, lots of material being subducted underneath it. And there were these huge subduction-related volcanoes, and then all the plutonic rocks that sit below them. So this would have been the kind of environment you would see in Japan today, where there's an island arc, subduction beneath it, and volcanoes on top. So that's quite typical in there. And then we also looked at the detrital zircon. So this is what a detrital zircon data set would look like. All the little peaks are different ages of zircons. So sedimentary rock doesn't just get material from only one area, it gets it from a lot of areas. Because if you think of something in a river system, it's going to sample all the rocks that it flows over. If you're in a little ocean basin, everything that's washing off that land is going to end up in your sediment. So we actually get quite a good idea of all the different ages of source terrains. And there's another little one. And I want to show you just a little blow up of Kelly's Mountain area, areas that you've probably driven through. And here we have more igneous zircons. So you can see the igneous ones are always sort of close together. They're one source. The detrital ones are more complicated. So here's two more detrital spectra. So these are a little bit different. So this one got a lot more 700, and this one had some extra ones. So we know from that that the sedimentation in even closely related areas isn't always the same. You can, again, think of a modern river system. You're not going to get exactly the same sediment all the way through. So that's something we have to account for. And then what do we do with that? Well, we have summary diagrams sometimes. So in this case, we have a band of zircons here. They're very characteristic of Northwestern Africa. And that's the age of the source terrain. That's where we think these are coming from. So we know from that this part of Cape Breton spent some time of its life right next to what's now Northwest Africa. We have also zircons that are associated with the Amazonian craton, which was, geologically speaking, really right down the road. And then we have some of these ages, and they're characteristic of what we call the Pan-African origins, when the supercontinent Rodinia was being assembled. So these are things that we can do with those data, because we don't want to just generate data, we want to actually do something with them. So we can use it to correlate units. So we can use these zircon data to look at Newfoundland and say, okay, how does that match up? Where are the same rocks found in Newfoundland? If you get ambitious, then you go over to Ireland or England and say, okay, where do those come from? So people are really interested in that sort of thing. So this is another little example of just a small data set where in that top one, you can see slightly behind our, no, I don't think I can move that. Never mind, that's fine. I think you can close it. Oh, now I can't do anything. Oh, there we go. So that little edge of the zircon data set there records a whole bunch of things. It records the subduction. So it has zircons from those ages. It records those Kelly's Mountain rocks that I showed you, that's a little bit younger. And it records a little bit of continental rifting from the same area. So you can have evidence for different events if you look very carefully at your zircon data. So in this case, this is all the sampling of old rocks. We don't really see much. This one really got all of its zircons from close by. So when you know the ages of things around your sediments, you can fingerprint them a little bit more accurately. You can try to figure out exactly where they match. So it's things that we can do with data. And on a global scale, what else can we do? Well, we can look at where little bits of Ganderia, this is that little bit of Cape Breton, where it started its life, what happened to it in different phases of it, where it eventually ended up, and what it was next to. So these are continental scale reconstructions that use some of that detrital zircon data. They also use things like paleomagnetism. They use other types of dating. They use a whole slew of things and try to put together what were our continents doing during this period. So we can go from really, really small things to some pretty large scale implications. We have the other part of Nova Scotia I wanted to touch on is the Maguma terrain. So this is where we are. We're here in Halifax. And if you've driven anywhere around Halifax, you've seen this big granite body. You've seen some of the rocks around it. Why is Maguma interesting? Well, Maguma is really fascinating because there's a lot of work that has been done on the mapping. It's really well mapped. That's quite well understood. And there's a bit of a mystery about Maguma. We sort of know where it came from, but we don't really know what it did between when it was formed and when it docked with Nova Scotia. So it's really quite interesting. It's also a lovely place to work. Really doesn't hurt to have field sites like that and beautiful metamorphic rocks with nice big minerals to work on. So there's a lot of really interesting things about it. And it's a peculiar area because it has lots of igneous rocks that intrude all of these sediments and make fabulous, wonderful minerals. So this is a little example of it. This is a staurolite crystal, and you can see that it's overgrowing a foliation. So when I put it in cross polars, you can really see it very well. So this is a regional foliation. This is a pre-existing foliation. So again, you can take small scale things and you need to make that rock form in a mountain belt. So you can go from micro scale to mountain belt scale. This one is neat because in this top one, there's only a few minerals. This one has an extra mineral right in here, this little green patch. And to us, it is chlorite. And chlorite is a characteristic mineral of lower grade metamorphism, retrogression. So when these things are being exhumed. So again, you can see your prograde history when it's being buried, and you can see its exhumation history. And the chlorite in this one is neat because it lives in a pressure shadow. That means while this rock was being exhumed, it was under pressure. So those new minerals will grow in low pressure areas. So again, it's a really neat sort of system of looking at things. So this is a little bit of Maguma history, where it started its life and where it ended up. So here's Avalonia. So this is part of Nova Scotia already. And this really is where Maguma started its life. Traveled across the Rhaeg Ocean. Here's Avalonia already, closer. Probably rifted away from Morocco. There's a project going on right now between several universities in Morocco, Nova Scotia, and Spain to look specifically at these pre-Atlantic connections between Morocco and Spain and Nova Scotia. So it's a really active area of research. There's a lot of people who are really interested in that. So a little bit later, they're closer together. So this is when we start seeing the Appalachians the way we know them. And eventually they're all together right in that middle of the supercontinent. And then of course, they rift away again. The bits in Morocco go to Morocco, and Maguma is stuck here forever. So we have the leftovers. So what about now? So this is history, 500 million year ago history, 1.2 billion years ago history. What about now? Well, every one of these rocks tells us something. So Hawaii, volcanoes, right? This is one of the most obvious things that we need to understand is how volcanoes work, right? How do we live with volcanoes? This is what's going on there right now. I mean, it's pretty spectacular. And it's, again, it's the same process that's been operating all through Earth's history. We're just seeing it in live Technicolor right now. This is a pretty spectacular eruption. Here's the other one that's happening today, is Mount Semeru in Indonesia. So these two are very different eruptive styles. This one has flowy, very, very high temperature magma. These are typical of big shield volcanoes. This one here is explosive, right? This one's more like Mount St. Helens, so much more explosive, has pyroclastic flows. This one really is much more dangerous because this is the one that sits there and sits there and sits there and just goes boom one day. The other one, you get a little bit more warning. So we need to know about hazards. We need to know about minerals. This is Mount Etna and Volcano. This is Etna, this is Volcano. That's the town, right? So people are living with these geological hazards. It's not just the eruptions, it's also all of this yellow sulfur, right? Where does that sulfur go? Goes into the air, makes acid rain and things like that. So we need to understand what our systems are and what the processes are. We also need to understand what these rocks have in them. So one way to look at that is to look at lake sediments, because lake sediments will get you a very, very good sample of all the different elements that are in your rock. And if you're just marble or something, great, no problem. But what if you have uranium in your rocks? Well, then you have uranium in your drinking water. And again, I come back to this picture of metals leaching into a lake, pristine Arctic lake, nothing going on there, but you can still see the metal leaching. So it is really important to have a good handle on what our geology is, because that's going to inform how we use our land. And that's a really important thing to have a baseline idea of, because if there was a mine there and you see that, you're automatically going to assume, oh, it was the mine, right? It polluted the water. But if you know, no, that's actually natural acid drainage, then you know, then you can deal with it. Then if you put a mine on it later, then you know, is the mine making extra problems? No, great. Is the mine making extra problems? Yes, then you can shut it down. So it's a really important management tool to know what's actually around. And we can use this type of map. So this is just an example of lake sediments, and the reds are high silver values. So not only can you use this as a sort of planning and predictive public health type tool, you can use it for exploration, but it's really important to have an idea of what is there. What do we have to deal with? Nova Scotia, we think of groundwater, right? We think a lot of people are on wells, a lot of people use groundwater every day. And we always think about this sort of human contamination aspect. We think about urban runoff, we think about factories, gas stations leak into the ground. We sometimes forget that the rocks can be doing just as much damage. So there can be metals leaching out from your bedrock. There's going to be metals leaching out from your crystalline bedrock, from sedimentary bedrock, all kinds of different things. And in that case, how does that look in practice? So I'm just going to go back to Schefferville very briefly. This is a spring, just an artesian well. And so you see that color is not exactly what you'd want in your taps. So this is what's called a chalybeate spring. And it's groundwater that's coming through iron-rich sediments. So as the water is percolating through those big iron formations, it's picking up dissolved iron and putting it straight out into the water. So these are really quite beautiful. They're fascinating. And there's so much iron that they're actually cementing together the plant material. So this is a really great place to study glacial rebound and plant material, because you can go and pick that apart. The iron has kept it for you. It's prevented decay, and you can go and figure out, okay, what kind of plants were there 3 meters down? So you can use these, but it's, again, it's a natural process, but has some consequences. A couple of Nova Scotia examples. So this is the provincial uranium risk map. So you'll see there's a few areas. So the green here is high uranium risk for groundwater. So if you're on a well in these areas, you can absolutely do test for E. coli, but you should also be looking at some of the metals. And why do we have metals in that? Well, the big culprit usually is uranium, which also radon. Everybody's favorite radioactive gas. So radon is actually a decay product of uranium. And Here's the reason. Our giant South Mountain batholith here, almost exactly the outline of the high-risk uranium, which is not unexpected. That type of granite can very often have uranium far above background levels. And it's not to say don't use it, don't build on it, don't live with it, but be aware of it, right? You can't change every hazard, but if you don't know where the hazards are, then you can't deal with them. So then you wake up one morning and you have radon in your basement. Not a great feeling, but you can actually check out radon detectors from almost every public library in Nova Scotia has them. So they're great, absolutely worth playing with. Here's another one, radon in indoor air. So radon being a decay product of uranium, if you have high uranium, you're also likely to have radon. And again, the big bullseye areas are right on our South Mountain batholith. So it's just, and same area, Cape Breton up there that had the uranium also has the radon risk. And here's our South Mountain batholith. It's right in the bullseye. And of course, no talk in Nova Scotia is complete without a little bit of karst. So karst is what happens when you have rocks that are soluble. So in the Mississippian period, Nova Scotia, specifically the Windsor group, all those nice gypsum things that you drive by, was a real sort of depot center for large evaporite deposits. And they actually call it a giant. It's a saline giant. It's a huge, huge volume of the soluble material that precipitate out of salty seawater. So there's a lot of it around Windsor. In fact, it's named after Windsor. And this is what it does. So any soluble rock will sit underground, it will gradually dissolve, and one day you wake up and you have the Oxford sinkhole. So last year, I believe you had a lovely talk about the Oxford sinkhole. That's the scary LiDAR image. So this is not something, again, that we can change, but if we know where the hazard is, if we understand how it works, then we can do something about it. So what do the rocks tell us? They say, listen to us, we have stories, we know things, we can tell you. So as long as you listen, we have something.